Okay, good evening, everybody. I'm Chris Lambell from the Electrical Engineering Group. So a couple of upcoming events. On August the 11th, we've got Kane from Enesis talking on battery technologies, and I've seen a bit of his presentation, so I know it's a pretty good one. That's also my birthday, by the way, so if you want to send any gifts into Chris Lambell, Care of Engineering New Zealand, that's appreciated, but not expected. 1st of September, we have Gallagher back in again, talking on electronic locks and credential types, different card technologies and the likes. But tonight we're here to talk on lightning protection, and we have Richard Walker. Has probably been in the industry, I don't know how long you've been in the industry, Richard, but all the time I've been in New Zealand, which is since 2005, and always been my go-to guy. Talk on lightning protection. So it's a usual format for those who've been here before, but we'll try and hold questions to the end. Come the end, we'll pass the microphone around the room for any questions in the room. We'll then read out the questions online. The usual rules, we're all here to share knowledge and ideas. We're not here to score points, so if anybody's asking any gnarly questions, then we'll draw it to a head pretty quick. If you do think you know more, or if you think you know something else to talk on, then you're more than welcome to come and talk here. Definitely a forum for it, so I'll hand over to Richard. Thanks, mate.
Okay, thank you, Chris. Okay, thank you, Chris, and thank you, Holly, for sorting me out with this. Lightning protection. I will get the right button here. So I'm Richard Walker and I work for Helios Power Solutions. I'm the AC Products Manager and I've represented Aeroco and formerly Global Lightning Technologies since the mid-90s. Just a little bit of history so you understand where you're coming from. Before I was with Helios, I was with Enertech Power Solutions, which was formed in 1987. So there's a few of you out there who will know me from there. And we developed a strong business in the New Zealand market for AC UPSs, primarily Riello UPS, power quality solutions, and lightning and surge protection from Invent Aeroco. We became part of Helios in 2016, and that's when the Enertech name disappeared. Helios was formerly Innovative Energies, also formed in 1987, and they have designed and manufactured a range of industrial grade power supplies, chargers, DC-DC converters, etc. And in the mid-1990s, the company moved to their current factory in Henderson. The name was changed to Helios Power Solutions in 2016 when other businesses were brought into the group. This is all about the lightning protection which we source from Aeroco. Aeroco is owned by Invent, hence Invent Aeroco. And so although I can talk to you about products, I can also talk to you about general principles, and that's more the point of this exercise tonight. So that you can understand where Aeroco has their expertise from, I'll just quickly run through their history briefly here. It's in 1903, they formed the Electric Railway Improvement Company in the USA. And in 1938, CAD-weld was invented. I mention that because quite a few of you will be familiar with CAD-weld, which is exothermic welding. And in 1951, that process was adapted for use in grounding connections. In 1975, a completely separate company at the time, Global Lightning Technologies, was founded in Australia. And in 1977, they developed surge reduction filters and transient barrier concepts. They set up their factory in 1982, manufacturing surge protection products. And in 1985, they developed the Dynasphere concept. The Dynasphere is an active lightning protection terminal, and there are a lot of them installed around New Zealand and the world. In 1991, Aeroco formed Aeritech, manufacturing galvanized and copper bonded ground rods, which is very commonly used in anything electrical and protection wise. In 1997, Aeroco Lightning Technologies was formed by the merger of Aeroco and Global Lightning Technologies. So that's when the two companies came together. In 2015, Pentair acquired Aeroco. So until that point, Aeroco was a privately owned company. And then in 2018, the electrical brand split off from Pentair to become Invent. And there's just a little note on the bottom there that showing you how large Invent is, 9,000 employees throughout the world with $2.1 billion in sales and operations over 80 global locations. And this is just an indication of some of their products, which you may have seen around the place. The left-hand box is the Caddy and Aeroco brands, and there's also Airflex, which isn't shown there. The other two boxes aren't really represented in New Zealand. So the focus of this is on the Aeroco side of Invent. And that's just a quick overview again. That's showing Aeroco back in the day working on railway lines when the point of it was to improve or make reliable electrical connections so that their electric railways functioned properly. Pretty good example of safety knot down on the bottom right there. Wouldn't be seeing that today. This is a range of the products that are covered, and they are relevant to the presentation today. They're grounding along the top row, CAD weld, and bonding, lightning protection, and surge protection. I'll be talking specifically about direct strike lightning protection, and coming under that is a bit of bonding and grounding. And will also be a bit of this presentation is on surge protection. Aeroco has a logical approach to all this subject, and that's called their 6-point plan. If you consider the 6 points in the plan, you should cover all your areas of risk as far as lightning goes. The first one is to consider whether you need to capture the lightning strike directly. And Holly, can I point to these pictures? It's not really possible with this, is it? No. Okay, then I'll describe it. At the top of the building there where the lightning is zapping down, oh, that's great, thanks, is a lightning terminal. That's an active lightning terminal, and that has a single high voltage cable going down to the earth system at the bottom of the building. And can we just go back to that? Oh, I can go back to that, can't I? Sorry about that. All right, we've got it. Right, around that building, so what I was just describing there is the active lightning protection system, the Dynasphere system typically, but not always. Alternatively, conventional lightning protection is made up of rods around the edges and across the middle of the building, and so you can see those around the top edge, and there are a number of down conductors going down to an earth system down the bottoms. So that's two approaches to direct strike lightning protection. Also shown in there are separated earthing systems, and there's bonding between them and bonding between the surge protection that's there. So that's an overview plan. But we'll talk in more depth about some of those things. Here is a world lightning map to show that there is certainly a risk of lightning throughout the world, not that you don't know that. And the scale underneath it shows the number of lightning flashes per square kilometre per year, with the right-hand side of the scale being the higher density. You can see in South America and central USA, central North America, I suppose, and some of Africa and some of Asia, it's quite a high level of lightning protection, lightning there, and at the top of Australia. New Zealand doesn't really show very well, but you can see a tint of sort of blue there and purple. We're not very high in the lightning density, but it's still a risk to us, that's for sure. Lightning formation. Lightning occurs when they get difference in charge between the clouds up there and also on the ground, the cloud electrification process. And eventually there will be downward leaders launched from the cloud towards the ground. They don't go all the way. Lightning is not a sudden zap from the cloud down to hitting the ground. You'll see at the bottom there that there are upward leaders being launched to try and connect with those downward leaders. When one of the upward leaders is successful, you have your lightning current path formed. An average bolt of negative lightning can contain 30,000 amps of current. This picture is taken from a photo out of the National Geographic magazine, which has been around quite a long time, the photo has. And you'll see that there's another upward leader being launched from the power pole next door to the tree, which was unsuccessful. You'll see also that there's multiple paths of downward leaders, but only one of them actually ends up being successful. Here is the actual photo. And so it's not just made up stuff that's quite commonly happened. You see a couple of upward leaders there, which are unsuccessful. And there's a lot of energy and heat where it has made the circuit, you might say. When we're looking at lightning protection, we have to assess the risk. If there was no risk of any of this, of damage or any adverse consequences, then it wouldn't be any point in spending money on lightning protection. We'll look at the structure dimensions, structure attributes, service lines, loss categories, environment, and protection measures. This is the risk assessment calculator out of the Australian New Zealand Lightning Protection Standard AS/NZS 1768/2007. It's an Excel spreadsheet that comes with the standard. And so Holly's going to help me here a little bit by bringing up an actual spreadsheet for a moment. Right, not the same spreadsheet, but you'll see there's yellow cells there, and some of those, we go through the different boxes, the blue titles there on the left are structure dimensions and structure attributes and environment. So we have to enter in the factors that relate to, or are applicable to that particular structure. In the middle, we enter information about service lines and other connections. And then on the right, we deal with loss categories. So on the left, as an example, if you'd like to hold your mouse over that red corner, it should come up with a hint. Yeah, right. So that's to help you when you're filling in that spreadsheet. You put your mouse over those boxes. That's just telling you that that's the overall height of the structure that you've got to enter with reference to ground level. If we go down to the next box, there's a lot more hints there. The next box is the structure attributes, and this particular one is risk of fire or physical damage. And the options for you are whether it's explosive, there's a high risk of explosion, or whether at the other end of the scale there's negligible risk because it's all bonded metal. So you read that list and then move the mouse away and back and click on the box, and there'll be a drop down comes up. So if you click there, you use that to select your option. And so that's there's a lot of other ones there. If we go over to say service, go up to under the power line there, you've just simply got a choice of underground or overhead or no power lines coming into the place. So that's fairly simple stuff. If we go down to straight down to efficiency of building at the bottom, yes, there. Okay, we can't see that. That gives you the lightning protection levels that are the standard ones to be applied. So that's just an example of how this gets used. We'll go back to the PowerPoint show. So here we've got a hotel in Darwin. This is an Australian sourced presentation, and so on the bottom left there we put in the on the upper left we put in the structure dimensions, and then you enter in that example I gave you before about what it's made of and other structure attributes. Underneath that is the environment, and ground flash density is a figure that you put in there. I'll flick through to the next screen. Here's New Zealand. This map comes from the Lightning Protection Standard, and it shows the darker the colour, the more lightning is present. The West Coast has got the highest level, which probably comes as no surprise to most people. The unfortunate thing for us as a business is that there's not a lot of business on the West Coast. I'd like to see those dark colours up in Auckland, but there's still a bit of lightning activity in Auckland, and and the rest of the country though. Just be careful. The top of that scale says 0.6 is the flash density. If we go to the Australian map, which is also in the same standard, it's got similar colours, but the top of their scale is 12 flashes per square kilometre per year. So it's a lot bigger, 20 times the scale of the New Zealand one. So don't look at the two maps and think that they are comparable. Our top density is only at the top of their bottom mark on their scale. So not so much lightning here. I'll go back to that. The risk assessment, you also enter in down on the left there, bottom left, the environmental, whether other buildings are similar height or shorter or taller. Service line density, whether you're the only place on the end of the line or if there are a lot of others, because surges that are coming down the power lines, if you're the only destination for them, they're going to cause you a lot more damage than if there are a lot of other connections. In the middle, it's quite explanatory, I think. You put into what kind of power connections there are and other out and underground services. And then on the right, we have loss categories. Now, this is the relates down to the bottom of the spreadsheet there, where it's titled overall risk. There are 4 categories there, and these are the categories up on the top right. And that's where the first column under the dedicated risk heading is where whether you have an acceptable risk or an unacceptable risk. They've thoughtfully coloured it. So if the calculation comes out in red, then you have an unacceptable risk and you've got to do something about it. At the top right, then they look at loss of human life, and you enter in a variety of factors for that. Loss of essential services, so whether this affects an essential service, and if you're just a standard business, it won't be considered to be an essential service. Another one, which often we don't have any figure entered in for, is loss of cultural heritage. But if the structure does have cultural heritage, it can significantly affect the outcome of the calculation. And the economic loss, that's a bit of a funny one. They have an acceptable risk of economic loss. We tend to, it says if unknown, enter in a particular value there. And I think a lot of people don't really know what to put there, so I'll leave it at that. You also enter in the fire-related damage factor. The fire is a significant risk of from lightning damage, because lightning can cause arcing and set your structure alight. Then we look at the protection levels, protection measures. The efficiency of building protection is actually whether you've got lightning protection already on the building. So that's going to be 0 unless you have some form of lightning protection. Then on the right, some of the letters have disappeared, but that's surge protection at point of entry, whether you've got that there, and then underneath that is surge protection at your distribution boards. And to the left of that is whether there's fire protection and whether that's manual, automated, or not at all. Right. If, as you can see in this one, if the loss of human life has come out as being red, unacceptable, and you'll probably find that if you were to put surge protection at your main board, that could change it. And if not, surge protection at your distribution boards as well. And if not, then put in direct strike lightning protection. But surge protection often has a significant impact on that result. Putting in lightning protection to the whole building is quite a large job compared to putting in surge diverters on a switchboard. So that's the risk assessment calculator. Protection levels are, we have a choice of 4 protection levels according to the standard, and the protection level is 1 is the highest and protection level 4 is the lowest. And the second column over on that table, if we go for protection level 3, which in the standard is set as a pretty typical protection level, considered to be standard, it's saying that 90% of lightning in the area should go to the lightning protection system and 10% may not. But that 10% is the weakest lightning protection. If you go to the protection level 1, only 2% may miss the lightning protection system, and that's going to be pretty weak lightning and may not really cause much damage anyway. The table on the bottom left tells you what current you can expect from the different protection levels and what distance they would cover. The putting lightning protection on a, well, first of all, I'll say that the New Zealand standard recognises just vertical rods, such as in that picture. Overseas standards often recognise they're a conductor laid on the building, Faraday cage type of arrangement, but flat on the building, and that's not recognised by the New Zealand standards. So we get engineers coming over here from the UK who are all excited about putting flat tape all over a building, and then they find it's not compliant with our standard. We have at Aeroco 2 systems that we can offer. One is the flat tape system, which is the left-hand table, and the other one is this woven conductor system. Here's some flat tape, 25mm by 3mm, and it's fairly robust stuff. This is joined together for a CAD weld. I haven't brought that along so much for the, if it's a bit longer, you can bend it, but it does take a bit of work to install it. And this is the woven conductor, and it's a lot more flexible, but it still sits there quite nicely. The woven conductor is from the US market, and the flat tape is more from European and UK market. Both systems have slightly different sized lightning rods, but with the, let's see if this next slide has got more information. Okay, we use the rolling sphere method of placement, which is where you have a large ball, typically 45 meters radius, that's for the protection level 3 or 90 meters diameter, and roll it along the structure. We'll say this is a building, sorry, roll it along the ground, and where it touches the building, then that building is deemed to be at risk. So you put in little rods there, and the sphere touches the rods and not the structure, and the structure is then deemed to be protected. There's this table shows you how far apart those rods can be depending on their height to give you the required level of protection. And as I said, the right-hand tables for the smooth weave conductor system, which has got rods that are 610 millimeters tall or 914 or 1.21 meters, whereas the flat tape system is rounded at 0.5, 1 and 2 meters. The reason for that is metric system for flat tape, and the US uses imperial measurements, so they're actually based on multiples of feet rather than millimeters. And I should say, if you are using a different size rod, you can apply that formula up the top left there to determine their spacing. This is the logical process for designing a direct strike conventional protection system. First, place your air terminals on the most vulnerable parts, which are the external corners and the high points, and then apply that rolling sphere method to place air terminals between them, or use those measurements in the previous table. In the flat surfaces between the edges, the standard allows that you can use the largest distances between the rods. And at the bottom of it tells you that that mesh method is discontinued. It was established by Architects and Surveyors Institute in 1905. They managed to get their influence in there because they don't like rods sticking up all over pretty buildings, and by putting in the flat conductors, you can't see them, but they are not so effective. Once you've put in your rooftop network, you interconnect all those terminals. Each terminal should have a connection in at least in 2 directions, and then that forms a network on top of the building, and you just treat it as a rooftop network. You've then got to connect that network to the ground, and there are rules for down conductors. Our standard says that down conductors shouldn't be spaced more than 20 meters apart, and they should be on all external corners. So you place them on your corners, and then you put them in between so they match that requirement. The European standard, IEC 62305, has a different spacing depending on your lightning protection level, whereas we don't. So it's a little bit simpler for us. You can use the structure itself, such as rebar in the walls or building columns, but that should still be around the external part of the building. And at the bottom, if you are using the building rebar, you've got to bring it out using Ricons or something like that to your earth electrodes. This is common components. You can see flat tape and joiners, splicers. The woven conductor system is at the bottom there, and that has quite a large base. That base can be fixed to a structure using adhesive, which overcomes corrosion issues with the roof manufacturers, which could be a problem if you drill holes in them to screw down your bases, and it also overcomes water leakage issues. So it's quite handy, and I've never known one in all the years I've been doing this to come unstuck. We have seen rods snap off, but not bases come unstuck. The materials commonly used are bare copper, tin copper and aluminium. And that's an important consideration because of galvanic corrosion between the lightning protection components and the structure materials. So if you have a zinc aluminum roof, you'd go for aluminium. And if you've got a membrane roof, you could use probably whatever you like, but more likely tin copper or copper. If you can get away without using any of these components, the structure can be self-protecting. If you're happy that lightning strike that melts metal is not going to put a hole in your roof, or if it does, it doesn't matter if your roof leaks. The wording underneath that list says that steel roofs need to be 4 millimeters thick to avoid puncture and 7 millimeters for aluminium. That comes from the IEC 62305 standard because the New Zealand standard isn't quite so specific about that. And that's saying stainless steel is not recommended by Bluescope, which is an Australian roofing supplier. AS 1768 2007 and 4.11.1 states where roof construction consists of electrically continuous metallic materials, such metallic roofs may form part of a lightning protection system, meaning you don't need air terminals. And in the appendix at the end of the standard, it gives you an example of what will happen if your roof is struck. A moderately severe lightning strike delivering a charge of 70 C would melt a hole of about 12 millimeters in diameter in a sheet of roofing iron, but they're not particularly specific. Well, they don't say at all how thick their roofing iron is, so it's just an indication, which is why IEC 62305 is a better reference. And this is a table from showing compatibility between different roof materials from the supplier and materials of lightning protection products. So they're saying there that zinc aluminum, second line down, zinc aluminum or aluminium coated steel, you can use zinc coated steel and zinc materials on it. You can use aluminium materials on it, but you can't use bare copper or brass on it. Traditionally, people think of lightning protection systems being made of copper, so it's good to keep this in mind that that's not necessarily the case. Connecting to the rebar, this is showing the Erico product. In New Zealand, we have a product called the Rycon that's made at a factory in Auckland and has been around for decades, so we don't import this other one because the Rycon factory is also the Erico manufacturer of Erico's CAD weld and so on. But that comprises of a steel bar at one end, the top left end of that picture, and that can be welded to your rebar because rebar is difficult to CAD weld to. CAD weld, for those who don't know it, is an exothermic welding process for electrical connections, and it is maintenance free and the best connection you could possibly make for electrical performance. And ideally you would, in a situation where you're going to bury connections, you CAD weld it better than clamps. That can be argued, but but CAD weld to rebar can be difficult. So using the CAD weld connection of the steel tip of or the steel lug, they call it, on the end of that cable, CAD weld that to your normal green earth wire, and then at this end there can be a terminal block or terminal plate that can be set into concrete, so you can screw your earth connections to it, or you can get it with a bare tail at this end, so you can make your own connection with that green earth wire. And this slide's got a mention of surge protection. Surge protection is an important part of lightning protection. As you may recall from the risk assessment calculator, surge protection can be applied to the switchboards and can make a very significant difference to your risk assessment. But I will get further into surge protection in the next show. This does mention building attributes a little bit. And challenges they may provide. So if you've got a building with a central core and the lift runs up the central core, and perhaps you've got an glass outer, it's difficult to run down conductors around your outer, so that can be a challenge complying with the lightning protection standard. You can't run also down conductors up the lift well, that sort of thing, so that's another restriction for not using the inside. It does say here that curtain walls could be bonded to the lightning protection system and can be used as down conductors if continuous, though, so that's an opportunity. Other challenges, lots of sensitive electronics in your building. On the top right, there's a swimming pool, so you can't put lightning rods in the middle of that, so you can't be compliant with the lightning protection standard with that sort of situation. On the bottom left is a simple but complex type of structure, which could be better protected with an active system, which we'll go into soon. And on the right there is a glass covered building where the architects won't want down conductors or running down over those glass panels. Excuse me. So now we've covered quickly the conventional protection from our standard. I will also note, this is the standard. That's what it looks like. This one's fairly well worn. Holly, can you just show me that other page that I've just got sitting there? There is a draft. This is 2007. There is a draft out for the latest version, which I haven't got to read yet, but I just thought I'd show you that it exists. At the moment, that's an Australian standard. It's got an AS number, whereas this one is an AS/NZS, and it hasn't been made clear to me if NZ is going to be in this new standard or not. I was told that we hadn't had participation in the committee, so I don't know how true that is, but keep an eye out for the standard. Thank you, Holly. So now we move away from the standard largely to active systems. An active system needs just one air terminal to cover a large area. Larger buildings will need more than one active system on them to be fully covered. We'll start off with the ESE air terminals. This is Ereco's System 1000, and ESE stands for Early Streamer Emission. This is designed according to the French standard NFC 17-102. And on the right there, you'll see that's the Ereco products, but this is made by a wide range of manufacturers around the world. I guess it's, I don't know why there would be so many people making it, but it's probably, it's a standard that promises quite a lot, quite a high performance. And the standard, NFC standard, requires a minimum of 2 down conductors. One is a dedicated down conductor, and the other one can also be a dedicated down conductor, or could be just a building structure. And it also requires you to bond nearby metallic features. Those down conductors that they've got there are not isolated down conductors, so your lightning currents are still going to be put into the building. And but the French government had a lot of these on their building, and they noticed that they were getting bypassed and getting a lot of strikes on their buildings. So they instigated a report called the INERIS report, which found that indeed there were a lot of misses, and this lightning protection method wasn't as reliable as it should be. So they recommended that a proper study be made into reviewing the whole design, and in the interim that the performance of it be downgraded. And on the bottom line in the red bar, you'll see the INERIS report recommends a 40% derating of that standard. As it happens, there are so many manufacturers, nobody's prepared to pay for an independent report, and one has never been done. But this lightning protection method promises, you put one up in a huge building and it promises the whole building to be protected. If you'd like to put your faith in that, it's a lot cheaper to buy one of these than other methods often. So they're certainly going in, but I'd be wary. And if you do have a serious lightning protection requirement, certainly pay close attention as to whether you would recommend or whether you'd use one of these. There are a number installed around New Zealand now. The other active system is the one that has been going in for many, many years, ever since I've been representing Erico and GLT, and that's the System 3000 with the Dynasphere air terminal. It is used normally with an insulated and screened low impedance down conductor. The thing about this system is that there have been peer reviews done on it where they have studied multiple installations around the world and recorded that the performance of the system is better than what's actually claimed. So these field surveys are available for study for anybody who wants to look at them. And the collection volume method is used to place these air terminals. This table just indicates the performance of the down conductor. The right-hand column shows the cable voltage developed at the injection point. Now, in an ideal world, there'd be no resistance or impedance between the cloud and the earth where the lightning current is got rid of, you might say. In practice, when it hits the lightning protection system, there is an impedance between that strike point and the ground. And so you have if you think of lightning as just being a huge current source with no voltage, the voltage is determined by the impedance of your lightning protection system. And so a low impedance cable develops less voltage. There is another supplier of lightning down conductor cable like this out there, and they say that their cable has a high voltage rating. So that's great, but it needs a high voltage rating because it is a higher impedance. Your ideal is to get the minimum impedance possible. So our cable with a lower impedance has a lower voltage rating on it as a result. And you can see here that if you have, for instance, this goes on to highlight there, a 30,000 amp peak current, that develops 44 kV at the top of the down conductor. However, if you're using a conventional down conductor, which is this sort of thing, then you're developing 19,000 kV. So there's a tremendous amount more higher voltage up there. And that's the benefit of the design of the high voltage cable. If I just go back to that system, we do supply that system with that high voltage cable, so we only need one, and it becomes an isolated system that can protect a large building. And so it is a convenient means of protection if you need something like that. I've been going for 15 minutes. I've got 15 minutes left. All right. Okay, time flies. So the Dynasphere, it works by having a earth central point and a sphere around it, which is isolated from that central point. That is coupled to the charge building up in the cloud, and there's a discharge network built into there, a resistor and possibly a capacitor in there. And so that allows it to build up the charge so that it launches the upward leader that I was describing earlier at exactly the right moment that the lightning was ready to form anyway. That way, this is not creating lightning when it's not necessary, and it becomes the preferred path for the lightning strike. This is just an explanation of the collection volume method. It's a complex calculation, and we use software to determine how that's what coverage is given. And the software is proprietary. We feed in the dimensions of the building, and it models it as basic building block such as that. I am going to shoot through these points quite quickly. This is an example of the use of a Dynasphere system or System 3000 on the, in this case, it's a radar site, and it allows the protection to be applied without interfering with the radar. It's very hard to put conventional lightning protection on it, something which is going round and round and round. So this can sit just beyond it, and it sits inside the radar focal point of the beam. And this is an example of a application in Australia where they put it on a desalination plant, but we won't dwell on that. And other examples of complex buildings where the System 3000 has been used. I will note a couple of other things before we go on to the surge protection. Bonding is important for conventional protection. That's typically a bonded system, and the point of that is so you don't get potential differences between the lightning protection and the structure. By having a large potential difference, then that encourages flashover and fire. And downconductors shouldn't be run in combustible cavities because there is the risk of flashover there despite all that. And the earth resistance, we're aiming for 10 ohms of total earth resistance. In a conventional protection system where you've got multiple earth electrodes, that's the earth resistance of the entire earth network. It can be through the lightning system itself across the building if you haven't interconnected all the ground rods. But if you do have otherwise you can put in a buried ring conductor interconnecting all the ground rods, and that's the best sort of system. It reduces your earth potential rise between the different points, spreads out your currents a lot more. But of course, when money's involved, it's not always desirable to dig a big trench and fill it up with copper. So sometimes it's been done, sometimes it's not. If I was building a data center, I'd be certainly more inclined to have a buried ring earth. Telecommunications, though, facilities such and data centers with sensitive electronics, the target resistance is 5 ohms according to the standard. Right, so that was very quickly through direct strike protection, and now we'll go very quickly through surge protection. One of the important things about surge protection is standards, and there are a lot of standards out there. This was an overview of some of the points of this presentation. We're not going to get to dwell on a lot of them, so I won't dwell on that at the moment. But we have got, there are a number of different standards out there. ASNZS 3820 2009. Oh yeah, that's a bit more about it. Essential safety requirements for electrical equipment. And that next standard was withdrawn according to the slide. We've got wiring rules, installation of surge protection devices, that provides information on that. Down the bottom of that page is ASNZS 1768 2007, which is my main focus for lightning protection and what we've been discussing. That sets out guidelines for protection of persons and property from hazards arising from exposure to lightning. Surge protection devices, that's SPDs, and while these are examples of some of the surge protection devices from a DIN rail product, which is what most people think of, to this is a box with DIN rail products in, but it's got other things which I may touch on if I have time. And this is a tried and true panel mounted surge diverter with big terminals and a gauge on it, which is a very well performing one for construction reasons, and that's been around for a couple of decades I think now. It's a very robust product. Anyway, SPDs should be installed after the main switch or isolation switch, but prior to any RCD devices. They should be protected by an appropriate fuse or circuit breaker, separate from the surge protection device, and they should be connected at the main switchboard from each phase to neutral. The figure shows a typical connection of this primary surge protection device, and I can see it better if I look at the big screen. I probably got out of the camera there. But we've, oh, sorry, yeah, you can't, I can see it. So we've got a surge protection device from our phase down to the neutral and a fuse protecting it. That fuse is protecting the wiring to the surge protection device. And at the main board, you've got the connection between the neutral and earth bar, so you don't need a surge diverter that has surge protection in there. I've seen them specified by consultants before where that is included, so that's just a waste of money because they're shorted. I don't mind selling them, but more money for me. And at a distribution board where you're away from the MEN link, we put in a surge protection device between there. This is showing a gas arrestor, but it could also be just a MOV like that. And quite often that's what's used in New Zealand. International standards include UL, which is not particularly recognised in New Zealand and Australia. That's a safety standard largely. And IEC, New Zealand standards are quite closely aligned. Sometimes some of them are with the IEC standard. They're very similar in some regards. That's IEC 6305. We'll carry on here. That's just showing you some of the IEC standards numbers. And there's this slide relates to classes. You'll see that there is, I don't know if this is the best one to, the top slide shows you two lines, class 1. Now, surge diverters are tested using a industry standard waveform. There's two standard waveforms out there commonly used. That's the 10 by 350 microsecond, where it has a 10 microsecond rise time and a 350 microsecond decay time, and the 8 by 20, which has been commonly used in New Zealand and Australian standards for many years. And they haven't, the European standards have recognised class 1, and possibly that will be more recognised by our new standard. Don't quote me on that though. Class 1 is used for rating surge diverters where there's a direct strike lightning protection system installed on buildings or where you have extreme exposure. There's more energy in a 10 by 350 microsecond waveform than there is in the 8 by 20. Class 2 is used for lower exposure main switchboards and for distribution boards. The main function of a surge diverter is to divert the lightning surge to earth. It needs to be rugged and to handle large surge currents, and so it needs a good surge rating. It needs to reduce the voltage seen by the equipment to a level that doesn't cause damage. No surge diverter is perfect enough to stop any of the surge coming through, so it's how much of that surge goes through that's the thing that we typically look at. We will, right, here is a table from IEC 62305 telling you what surge current you can expect from a, so on the site you can expect a, if we look at the top right system cell there, under the lightning protection level 3 heading, you'll see that it suggests a peak current of 100,000 amps will hit your structure. That's the 10-350 microsecond waveform. And if I go to the next slide, so if you take that figure and the lightning is hitting the lightning rod on top of that structure, you've got 100,000 amps flowing down to earth, but they're suggesting that a portion of that will get to your electrical system, and they're suggesting that a quarter of that will be on each phase. So you've got quarter going, sorry, I'm getting just thinking my maths here, 12.5. Half the lightning of the 100K will go to earth and half of it will go to the electrical system. So that's 50 Ka. And if you've got your 3 phases, you end up with about 12.5 Ka per phase, which is why the surge diverters are commonly rated at 12.5 Ka once all those currents are split. That's an example of the surge waveform, which I've just described. And again, I won't, because time's going pretty quickly, I won't dwell on these at the moment, but there's a lot of figures behind the surge protection ratings. Now, these are the classes and where they're used. So this is the more information that you'd be, that's specifiers will be writing in their specifications. Class 1 or 2 can be used at the point of entry there. If you've got the direct strike lightning protection on that building, if you're following the IEC standard, you'd apply a class 1. If you're following our New Zealand Australia standard, you wouldn't bother with calling it class 1. You would just put in a large surge diverter. There is a table in the standard which recommends that for the point of entry you should use 100 kA rated surge diverter. At the distribution board you should use 40 kA is what's stated in the standard, although a lot of suppliers, including us, have got 50 kA as their standard size for that now. So this is a 50 kA or 50,000 amp device, not particularly large, and that clips on the DIN rail, and if I unclip that, a replaceable module which has got a status indicator on it so that you can see if it's been consumed. Because this is metal oxide barista, it does get consumed as it handles surge current, as it conducts surge current. That's just a table suggesting what you should put where. And that's an example of different surge diverters. So this one here is a single phase one. For 3-phase systems at the main switchboard, the 3+0 example provides a surge diverter for each phase only, as explained on that earlier slide, and as shown here on the diagram on the right. And the 4-module surge diverter can be used for distribution boards. So the 4th module goes between neutral and earth. Series connected surge diverters, otherwise known as filters, put an inductance in series with your load current. This is showing your voltage protection level when one of those is used. So UP is the voltage that's allowed through after the surge diverter is acted on the surge. And for a typical spark gap on the left there, you'll see that that still lets through about nearly 2,500 volts, which is quite high. A typical metal oxide varista would be more like 1,600 volts, and a typical surge filter is right down at just over 500 volts. So they're particularly effective, but they are relatively expensive because you've got to size them according to your load current. And that's an example of a surge filter and a waveform. I won't spend time on that. What I will note is temporary overvoltage. If you're on a power supply where the supply voltage can rise higher than you would normally expect, so instead of being 230 volts, it's up to 270 volts briefly, that can burn out a surge diverter. That can happen at the end of a working day when industries drop all their loads and before the transformers switched, so the supply voltage does jump right up. A standard surge diverter could burn out. This uses a technology which discriminates between the very short impulse time of a standard surge and the long time of a standard AC waveform, and it won't conduct the AC waveform, but it will still suppress the surge, conduct the surge. So that's a technology, transient discriminating technology, which can be used in those situations. They also mean the surge diverter can last longer because they're not consumed by little brief overvoltages. We won't dwell any more on this today, except this was a slide showing one of the important things is thermal disconnect. So metal oxide varistas, when they get consumed, they'll go short circuit. So that's if a temporary overvoltage is there for a long time, or if they've just been working for a long time and consumed a lot of surges. In the old days, early days of MOVs, they would then catch fire. So you do see people I've seen 1 or 2 people wanting them to be in boxes, metal boxes, because that's what they've experienced in years gone by. That doesn't happen, I would say, to any surge diverter on the market these days because they've got internal fusing. This slide, if it works, will just show you the tests that they run, where the right-hand meter is the voltage that's applied and the left-hand meter shows the current that will suddenly will take off when the surge, when it conducts. So can I run that from here? Nope, it goes to the next one. What happens if I push the play button? Does it? Oh. Should I just? Good to have you here. Right, there's the voltage is rising, and you keep watch out for the smoke in the middle. And that's a sprung-loaded fuse inside, trips and disconnects them off. So that's the internals, and so that's for internal protection to prevent this from going up in smoke. It is not the same as the external fuse, which is needed to protect the wiring going to the surge protection device. There are a number of parameters to specify for a surge diverter, including the maximum continuous operating voltage, which is the maximum voltage that it will keep working at without burning out or being consumed. The UP is the voltage protection level, which is what it lets through to the load when there's a surge. That's based around a specific size test current, test surge, and all surge protection manufacturers should use that same test waveform so that you can compare apples with apples, ideally. I impulse is the surge rating, class 1 surge rating, and that's saying that it will take a quantity of 15 of that size surge before it fails. And IN is the class 2 surge rating of the same thing, the size surge it can take 15 of before it fails. IMAX is the single shot surge rating, and so those are important factors. When you're specifying surge protection, it would be good to see that written into the specification, what you're after. Typically though, what a specifier would do is they would be visited by people like myself and, dare I say it, my position, and use their products to write a specification. So it's important to realise that that's not always the only way to go. It should be taken as an example. And that's what I've shown you before. That's a surge filter or series connected device. You can see the inductors inside there, but it's still got shunt diverters in it as well. So it adds these inductors to the shunt diverters. Modes of protection. On the left is at your main board where you've got each surge diverter down to your neutral earth bar. At your distribution board, you have those 3 surge diverters to your neutral, and then another surge diverter down to the neutral earth bar. And you could conceivably put surge diverters from each phase to earth as well, and that's the way it used to be done, but it's been determined that that's not essential and it's not cost effective. And it's an alternative to the middle one. You can have a surge diverter from each phase and from neutral to earth. This is examples of where the surge diverters can be applied. And so we're not talking just about main surge protection. We can put surge diverters on the telecommunications and on signal lines that are going out into the field as well, on PLCs and modems. This is a bit about fusing. So the fuse to the surge diverter you don't necessarily have to have a separate fuse going down there. You could just use your supply fuse if it's within the required sizes. For a standard surge diverter, the standard says that 32 amps may be used, and typically up to 100 amps would be used, so somewhere between 32 and 100. It's conceivable that if you have the lower 32 amps, they could burn out or trip if you have a very large surge. In practice, I haven't heard of that being a problem. But to be on the safe side, 63 amps is a good compromise, or 100 amps. These particular products have larger terminals, and you can actually use up to 315 amps protection on a 25 kA fault rated switchboard. It may be desirable to have the protection in there anyway for convenience, so you can actually work on that circuit. But that's just saying what I just said. Wire length is a very important factor though. If you do, you need to keep the wire length between here and your bus as short as possible. It can develop about 1,000 volts per meter. And so if you've got 1 meter of wiring between your surge diverter and your supply, then you can lose 1,000. It makes the surge diverter 1,000 volts less effective. So if your surge diverter was going to let through 1,500 volts of the surge to your load, and you have an ideal direct connected situation, and you have a 1 meter piece of connecting wire in there, it suddenly lets through 2,500 volts to the load. I've had one situation I remember where I supplied these top performance surge diverters, and they came back to me a few months later and said our gear's been damaged by surges. And it turns out the supply was in the top of the cabinet, and the cabinet was about 2 meters tall, and they put the surge diverter in the bottom. So they ended up with 4 meters of cabling. So that's 4,000 volts of less effectiveness of the surge diverter. If you're putting in a protection device, that can add to your length. So just be wary that you need to put that in a convenient location. That's an example of how not to do it, where they've retrofitted a surge protection device and got lots of cable length back to the switchboard. And so this is an example, actually it's what I've got here, just different surge diverters. And those are filters. There's a little DIN rail mounted filter on the left and larger cabinet mounted filters in the center and the right. And these are surge protection devices for things other than power. On the top left is a barrier, could be used for 4 to 20 milliamp loops or small signal applications. A DC surge diverter on the center there for 12 volts or 24 volts. Coaxial surge diverters on the right. Underneath is a phone line surge diverter, pluggable, and chrome block surge diverter in the center. And on the bottom right is a LAN surge diverter. The 6-point plan, I'll just run through the points. That's the picture I showed earlier at the beginning of the presentation. Capture the lightning strike, or consider if you do need to capture it or not. And if you do, then work out how you're going to convey the energy to the ground. So what conductors you're going to use and where you're going to position them. Then point 3 is how you're going to dissipate the energy into the ground. So you're looking at your earthing, look at your ground type. If you need to have enhancement there, if you need to use, ideally you'd do a soil resistivity survey where you'd measure the resistivity and determine if you're going to use horizontal conductors in the ground, or you might need to use deep driven. If you're on a high pedestrian area, you may want to use the deep driven electrodes and put insulation at the top so it doesn't have earth potential rise where the pedestrians are. You need to bond all your points together, and you need to do it not daisy chain, because you end up with lightning currents going through different devices. You've got to go all to a common bonding point. Then you consider protecting your incoming AC, and then you look at protecting your low voltage data and telecommunications. So if you cover all those points, you should be properly protected. That's the picture. I won't stay on that again, because I would imagine we're minus 10 minutes now, are we, Holly? These are different examples of how surge and lightning protection can be applied. So in this situation, with the previous one, just a general one, but this shows a telecommunications facility and industrial rail